Oh, okay. We started already. So, shall we start? Let me briefly introduce the speaker today. Welcome, everyone. Today we have Maya Sankar from Stanford telling us something about the homomorphism threshold.
Cool. So I just want to say, feel free to ask questions in the chat or ask them out loud if I don't notice that there are questions in the chat, because I don't always get to see them. Would it be possible to make me not co-host, because I get a notification every time someone shows up?
Yes, okay, I will.
Cool. So I guess the question I want to talk about today is the following. So fix a forbidden subgraph H and a minimum degree constant delta. And we're interested in graphs with minimum degree fraction delta that are H-free. And the question is, which values of delta let us prove structural properties of G, or let us not prove structural properties of G? So like for which values of delta is the structure of G constrained? And as an example, I want to talk a little bit about triangle-free graphs. So if G is a triangle-free graph and we have n vertices and we have a minimum degree fraction delta, well, we know that if delta is strictly greater than 1/2, then it's impossible to have a triangle-free graph with minimum degree n/2. It's also true that if delta is at least 2/5, then G has to be bipartite. But at 2/5, something else can happen. G can, oh, I forgot to say, G is bipartite is the same thing as saying G has a homomorphism to K2. And then if we keep going, right below 2/5, G could look like a blowup of C5, and we can keep going in this manner. And the question is, can we keep going until 0? Is there a hard threshold? And it turns out that there's a hard threshold at 1/3. So below 1/3, there's a theorem that says that if G is triangle-free and has minimum degree, or there are graphs that are triangle-free with minimum degree fraction arbitrarily close to 1/3, but chromatic number arbitrarily large. So not only can we not get this nice homomorphism structure below 1/3, we in fact can't even show anything about the chromatic number. On the flip side, above 1/3, we can bound the chromatic number of the graph just in terms of the minimum degree fraction. So we call 1/3 the chromatic threshold of the triangle, the point at which we can start bounding the chromatic number of the graph in terms of its minimum degree fraction. So similarly, we can ask, when can we start describing this graph as having a homomorphism to some other graph? So we can say that when G has minimum degree fraction a little bit more than epsilon, not only does it have bounded chromatic number in terms of epsilon, but we can say it's got a homomorphism to some known triangle-free graph. And the point at which we can start making this structural guarantee is called the homomorphism threshold. So here are the, I guess, formal definitions of the chromatic and the homomorphism threshold. I won't read them out loud, but just the chromatic threshold is the point at which, if we have minimum degree fraction at least delta, then we can bound the chromatic number of the graph in terms of the minimum degree fraction. And the homomorphism threshold is the same thing, except the structural guarantee we get is that G has a homomorphism to some fixed graph, gamma. And one important note is that the homomorphism condition is strictly stronger than the chromatic condition. So if you have a homomorphism from G to gamma, then that also gives us a bound on the chromatic number of G. And so that tells us that the homomorphism threshold is always at least the chromatic threshold. So we now know the chromatic threshold for all graphs, but bounds on the homomorphism threshold are not known in all that many cases. So we know that the homomorphism threshold of the complete graph is equal to the chromatic threshold of the complete graph. And we know that the homomorphism threshold of odd cycles is at most 1/2r plus 1. We also know the homomorphism threshold of this forbidden family. So this is the same definition, except we're interested in graphs with a minimum degree condition forbidding all short odd cycles. And we're interested in having a homomorphism to a graph forbidding all short odd cycles up to C2R plus 1. But in general, we don't know how to prove lower bounds. So each of these results, the lower bound came from the, in this case, the lower bound came from the fact that the homomorphism threshold is at least the chromatic threshold. In this case, the lower bound construction is sort of a natural thing, and that's what led to considering this family C2R plus 1. And so a general question is, how do we show lower bounds on the homomorphism threshold? And do we know any single graph where the homomorphism threshold is different from the chromatic threshold? We do know families of graphs. This family actually does satisfy that, but we don't know this for any single graph. So I want to talk briefly about a proof that the chromatic threshold of all longer odd cycles than C3 is 0. So for C3, this, I guess, matches the pattern for other complete graphs. So I guess setting this up, we want to, I guess we have a C2R plus 1 free graph with minimum degree epsilon n, where I guess this is 0 plus epsilon n, really. And we want to bound the chromatic number of the graph in terms of the minimum degree fraction epsilon. So we choose a subset of vertices, which is maximal with the property that any two vertices in our set have disjoint neighborhoods. So because any two vertices have disjoint neighborhoods, the total number of vertices in our set is at most 1/epsilon. But also, you can check that the second neighborhoods of this set, of the vertices in this set, are going to cover all of the vertices of the graph. Because if there were some vertex that wasn't covered by any of these second neighborhoods, then we'd be able to add it to A. So the last step of this proof, which I'm not going to do out, but it's not super difficult, is to show that any C2R plus 1 free graph with radius at most 2 is 4R colorable. And using this fact, we can color each of the second neighborhoods with a separate set of 4R colors, and we can bound the chromatic number with 4R times 1/epsilon. So that's a proof that we've bounded the chromatic number in terms of epsilon, and so the chromatic threshold for odd cycles is equal to 0. And so I was able to show that the homomorphism threshold for odd cycles is in fact strictly greater than 0. And I guess this is the first known example of a single graph where the homomorphism threshold is strictly greater than the chromatic threshold. But the other reason I'm excited about this proof is because it has a topological flavor. And I got to, I guess, introduce this new topological notion of homotopy equivalence, which I'm going to talk about a little bit later. So the graphs that I used to get this lower bound are called Borsa Graphs. So this is a graph on the n-dimensional sphere where you connect each vertex to a small ball around its antipode. So one of the important properties about this graph is that it has small odd girth, because if you think about starting at a vertex and like taking a walk, you'd have to bounce around a lot before you could get back to your original vertex in an odd number of steps, because each bounce, each there and back again can't take you very far from the original vertex. So I guess the first property is that for sufficiently small epsilon, this thing is C2R plus 1 free. The chromatic number of this graph is bounded in terms of n. It's going to be at least n plus 2. And this is equal to the Borsa-Coulomb theorem. And the last property, which I'm just stating for completeness, is that we can get good approximations to this graph. And so we'll use these approximations to get a lower bound on the homomorphism threshold. So ultimately, our goal is going to be, we'll pick some n, and we'll pick n so that the chromatic number of this graph is large enough to derive a contradiction. And then we'll keep taking better and better approximations to this Borsa graph and show that as we take this sequence of better and better approximations to the Borsa graph, there is no C2R+1 free homomorphic image of all of them. So here's maybe some intuition of how the proof goes. So we'll fix n, which we'll determine later, and we'll consider some very, very good finite approximation to the Borsa graph. And let's suppose, for the sake of contradiction, that there is a homomorphism from G to H, where H is C2R+1 free. And because G can be chosen to be arbitrarily large, we can say that H is like arbitrarily small relative to G. So in particular, because H is small relative to G, and G has so many odd cycles of size 2r+3, one of those odd cycles is going to be non-injective under phi. Two of its vertices are going to get mapped to the same vertex in H. So in the C5 free example, G has a lot of C7s. And so because H is very small relative to G, one of those C7s is going to be mapped non-injectively. And then we ask, okay, we've started with this one C7, but we can perturb vertices to get other C7s in the graph. And the images of those C7s are also constrained. Basically, because G has been mapped non-injectively, we have a triangle. And that because we have a triangle in H, that means we can't do anything that would turn that triangle into a C5. So we have a lot of constraints on where these perturbed vertices can go. And we can keep perturbing vertices and keep being constrained. And actually, in the C5 free case, we can directly show that if H is the image of a bunch of these perturbations, where we started with some non-injectively mapped C7, then in fact, H has to look like either a copy of K4 or some three-colorable graph with a bunch of bipartite things glued to it. So in fact, we get a very strong structural property on H. And then we can get our contradiction by choosing n large enough. So we know H has chromatic number at most 4. So that means G has chromatic number at most 4. But G is a really good approximation, so the chromatic number of G is the same as the chromatic number of the Borsa graph. And if we choose n at least 3, then phi cannot exist, because if phi did exist, then G would be 4-colorable. So that's how we derive the contradiction. And for larger odd cycles, we can't directly bound the chromatic number of H. But what we can do is we can pick a subgraph H prime of H that sort of contains all the topology of G. And by contains all the topology of G, I mean the chromatic number of G is bounded by the chromatic number of H prime. And then we can additionally say, well, H prime has to be highly structured in some way. So I'm happy to pause and take questions about any of this if there are questions, or I'm happy to move on. So I guess now I want to tell you a little bit about the topological notions I used. So we want to formalize the idea that all of G can be obtained by perturbing a single odd cycle. And so I defined this notion of homotopy equivalence, which says 2 walks are homotopy equivalent if you can go from one to the other via a sequence of perturbations. So the first type of perturbations we allow are substitutions. So a substitution operation is one where we take our walk and we just change one vertex to a different vertex. So we change vertex vi to some vertex vi prime. And then the other two steps we allow are insertions, which add a there and back again step. So from vi, we go to some vertex w, then back to vi, and then continue as before. And deletions, which are the opposite of that. So if we have a there and back again step, we can remove it. And one important thing to notice about this is that parity comes up a lot with this definition. And one way in which parity comes up is that the parity of a path is always preserved under these operations. So an insertion will add 2 edges to the walk, and a deletion will remove 2 edges from the walk. And then the second notion from topology that I want to take is that of being simply connected. So a graph is simply connected, or a topological space is simply connected if any loop is contractible to a single point. So we can't say any closed walk is contractible because odd closed walks are never going to be contractible. But we can say a graph is simply connected if any even closed walk is homotopy equivalent to the trivial closed walk. And the Borsa graph, I guess this encapsulates the property that the Borsa graph has, that we can start from a single odd cycle and achieve the whole graph via perturbations. The Borsa graph essentially behaves like the topological space, the n-dimensional sphere. And a way to see this is if you have a walk in the Borsa graph, you can sort of continuously extend it to a path in Sn. And then if you have a homotopy between 2 paths in Sn, you can discretize that homotopy to a graph homotopy between 2 walks on the Borsa graph. So I'm waving my hands a little bit over that, but the idea is not only does the Borsa graph behave like the sphere, it's sort of it has the same, it's simply connected if and only if the sphere is simply connected, because any homotopy in the sphere becomes a homotopy on walks in the Borsa graph. So I guess using that fact, I can tell you the thing I actually proved, which is the following. So suppose we have a simply connected graph G, and we're thinking of G as being the Borsa graph or a good approximation to it. Let H be a C2R plus 1 free graph, and suppose we have a graph homomorphism from G to H. And suppose that the graph homomorphism is non-injective on some odd cycle of G. So this is not quite the same thing as being non-injective, but with the Borsa graph, all odd cycles have length at least 2R plus 3. So it becomes the same condition. Basically, we want there to be a short odd cycle in the image of phi. In this case, we can bound the chromatic number of G. And we can use this to prove a lower bound on the homomorphism threshold of odd cycles. So if you take, sorry, this should be 8R squared minus 2. If you take a bunch of increasingly good approximations to this Borsa graph with 8R squared minus 2 instead, then those approximations will eventually have chromatic number equal to 8R squared. And for any fixed C2R plus 1 free graph, those increasingly good approximations will eventually satisfy this property on some odd cycle. And so if we use a sequence of increasingly good approximations to this Borsa graph, they just can't have any finite C2R plus 1 free homomorphic image. And that's how we lower bound the homomorphism threshold of C2R plus 1. So I'd like to switch gears now and talk a little bit about some of the proof techniques I used. So one of the key observations is that C4s in this graph topological setting behave a lot like small open sets, in the sense that open sets are regions in which we can locally perturb a loop or a path in a space. Similarly, substitution lets us locally perturb any closed walk by taking two edges of a C4 and replacing it with the other two edges of a C4. So this motivates defining this thing called the C4 closure of an edge. And I've denoted it this way to, I guess the little diamond stands for C4. And this is the smallest set that contains the edge we start with, and then any C4 containing that edge, and then any C4 containing any of those edges, and so on. So it's the smallest set containing the edge that's closed under the property that if we take a C4 with one edge in the set, then the whole C4 is in the set. And C4 closures have a nice, I guess they have a really nice property, which is that they let us define homotopy invariance. So I'm going to talk about a couple of, I guess, mention a bunch of different homotopy invariants, but I want to prove at least one of them. So given, I guess we're fixing an edge, and given a walk in a graph, we let I sub e of p be the number of edges of p that are in the C4 closure of E. And we're counting edges with multiplicity because I guess walks can repeat vertices and repeat edges, and we don't want to lose that structural information. So this thing is actually a homotopy invariant mod, or IE mod 2 is a homotopy invariant. So let's prove that. Basically, we have to check that each of our three steps preserves the value of the invariant mod 2. So I guess first, insertions, we're adding a there and back again step. Then we're adding two copies of the same edge, v sub I w. So either v sub I w is in the C4 closure, in which case IE goes up by 2, or it's not in the C4 closure, in which case IE goes up by 0. And then a deletion is the opposite of this. It removes two copies of the same edge. So either that edge is in the C4 closure and we go down by 2, or that edge is not in the C4 closure and we go down by 0. And the last thing to check is that substitutions preserve this quantity. So if we have a substitution like this, then as we said before, that means that we have a C4 vi minus 1, vi plus 1, and v prime I. And if the C4 isn't degenerate, then the four edges of the C4 have to be in the same C4 closure. So either we took away two edges from the C4 closure and added two new edges from the C4 closure, or this C4 closure is totally disjoint from the four edges we're adding or removing. So either we're decreasing IE by 2 when we remove these two edges and increasing it by 2 when we add these two edges, or we're doing absolutely nothing because these four edges form a C4 and therefore belong to the same C4 closure. If the C4 is degenerate, then this is casework. Basically, you ask if vi minus 1 equals vi plus 1, or if vi equals v prime I. And in each case, it's a similar flavor to the first two bullet points. So you can define a bunch more homotopy invariants. So they all have the same general form, which is let A be a subset of edges, sort of like the C4 closure we considered earlier, and let IA of P be the number of edges of P that are in the set A. So once again, we're counting with multiplicity. And I guess I stands for invariant. It also stands for intersection because we're looking at the intersection with this set A. And I guess there are a lot of different types of homotopy invariants. The first one is this, the one that I talked about, before, which is if A is the C4 closure of a fixed edge, then this IA is going to be homotopy invariant. We can do a similar thing where if we take a graph homomorphism and we look at the pre-image of some C4 closure, and it turns out that almost the same argument I gave on the previous slide works here, except you have to be more careful about the degenerate case. You can also take connected components, and I guess this last trick is you look at the set of edges that are incident to some fixed vertex V, and that set also turns out to give you a homotopy invariant I. And I guess the only one that I'm going to be looking at for this talk is this one. But ultimately, having so many different homotopy invariants to choose from is one of the things that makes this theory useful. I guess the second useful fact that this theory has is, suppose we have a homotopy invariant IA, and suppose that we're working in a simply connected graph. Then homotopy invariants are going to be the same on all even cycles and the same on all odd cycles. That is, if IA is odd for one odd cycle, then it's going to be odd on all odd cycles. And if it's even on one odd cycle, then it's going to be even on all odd cycles. And this follows from the fact that all even cycles sort of look the same in a connected graph, and all odd cycles sort of look the same in a simply connected graph. In the same way, in a topological space, all loops look contractible. So I guess now I want to take some time to sketch the proof of this theorem that I put up earlier. So the first step is showing that the chromatic number of G is at most this, I'll talk about where this comes from in a sec, but basically bounding the chromatic number of G in terms of the chromatic number of the C4 closure of some edge in the image. So this is the, if you remember before, I said the chromatic number of G is at most the chromatic number of some H prime. This is the suitably chosen H prime that sort of captures all the topological structure of G. And so we required that this edge E also is on a short odd cycle in H. And the reason for that is because if E is on a short odd cycle, then if we keep gluing C4s to our edge E, the C4 closure has to have bounded radius, or else you can imagine if we kept gluing a ladder here, we would eventually hit the forbidden short odd cycle. So this isn't immediately obvious because you do have to worry about C4s that look like this, that I guess you might not have something as pretty as a ladder, but we get a constraint on the graph C union E, or C union the C4 closure. And the last step, this is reminiscent of what we talked about when we were proving that the chromatic threshold of any odd cycle is 0. You show that if your graph has bounded radius and is C to R plus 1 free, then actually its chromatic number is itself bounded. And the way this step works is you show that each iterative neighborhood is 2R degenerate. So I think I want to spend a little bit more time talking about how this first step works, how you can bound the chromatic number of a graph in terms of the chromatic number of some C4 closure, because I think this is the step that leverages the homotopy theory the most, and I think it's kind of nice. So I'm going to prove a slightly weaker version of this. I'm going to, instead of getting a bound of 4 or chi of the C4 closure, I'm just going to get a bound of 2 times chi of the C4 closure. So suppose that G is simply connected, and suppose we have a graph homomorphism like before. And let C be an odd cycle. This is going to be the odd cycle that's mapped non-injectively. Then we can find an edge so that the edge is on an odd cycle in the image of C. If C is mapped non-injectively, then any odd cycle in the image of C is going to have length strictly less than C. So this gives us the property that we want, that E is going to be on a short odd cycle in the image. And additionally, the chromatic number of G is bounded in terms of the chromatic number of the C foreclosure of E. So I think this is easiest to see in the case that phi is the identity map. I realize that's not quite the regime we're working in, but I think a lot of the proof ideas are the same, even in the general case. So when phi is the identity map, I guess we're just looking for an edge in an edge of C. So we can partition C into the different C foreclosures. And because C is an odd cycle, at least one of these parts is going to have odd size. So that is, C intersect some C foreclosure is going to have odd size. And that's the same thing as saying that this intersection, or this invariant, i.e. if C is odd. So then we're going to use the fact that all odd cycles behave the same under these invariants. So because G is simply connected, any other odd cycle is also going to have i.e. if C prime odd. And in particular, i.e. if C prime is going to be non-zero. So that tells us that if we cut this whole set, this whole C foreclosure out of G, the remainder is going to be bipartite. So in some sense, this C foreclosure captures all or almost all of the topological structure of G. And the last step is to observe that the chromatic number of G is at most the product of the chromatic number of two sets of edges that union to G. So the chromatic number of G is at most twice the chromatic number of the C foreclosure. And I wrote down a better bound on the previous slide. I wrote down, I guess we can go back. I wrote down a bound of max 4 and chi of the C foreclosure. So you can actually do better here. If the C foreclosure doesn't have any odd cycles, then this bound out here is equal to 4. But if the C foreclosure does have an odd cycle, then you can actually do better because we know what all the homotopy invariants are equal to on this odd cycle. And so, in fact, in this case, you can show that not only is E, you can show that any path in this graph out here has to be even if it's going between two vertices of the C foreclosure. And not only that, but it has to go between the same two vertices of the C foreclosure. So what you actually get is you get that G is equal to the C foreclosure with a bipartite graph glued to each vertex. So you get something way stronger than just a bound on the chromatic number. So that's what I was saying about how this C foreclosure captures all the topological complexity of G, because in fact, unless this thing is bipartite, it's just all of G, except you might have to glue some bipartite graphs to it. So in general, we want to do the same thing, but where we pick a homotopy invariant that works well for us. So we want to pick a homotopy invariant IA, which is odd on the odd cycle. And then we will know it's odd on every other odd cycle too. And we also want it to have the property that A is a subset of phi inverse of a C foreclosure. So I'm not going to talk about how you pick this edge and pick this set A, but this is essentially, this thing is going to be one of the other homotopy invariants that I put on the previous slide. And the ultimate argument we get is that chi of G is at most twice the chromatic number of the C4 closure, but the chromatic number, or twice the chromatic number of A, but the chromatic number of A is at most the chromatic number of its image. And once again, you can use the same trick to get a bound of 4 or just the chromatic number of the C4 closure by doing the same, I guess, slightly deeper structural analysis as before, and showing that in this case, you don't quite have a bipartite graph glued to each vertex of A, or you don't have A with some bipartite graphs glued to certain vertices, but you have something very close to that, where A still captures almost all of the topological structure of G. So I guess lastly, I want to switch gears a bit and talk about something, I guess, topological extensions. So the discrete fundamental group is constructed by taking closed walks based at some fixed vertex phi, and the group operation is concatenation, and two closed walks are considered the same if they're homotopy equivalent. So this is the same construction as the fundamental group, but using the notion of homotopy equivalence that I've given. And the same arguments from algebraic topology will show that this group doesn't depend on the fixed vertex phi that we choose. And this group turns out to be similar to the fundamental group of an associated topological space. So we're going to define the neighborhood complex of a graph. So this is a simplicial complex whose faces are sets of vertices with a common neighbor. So we put, I guess, a one simplex on any pair of vertices that share a common neighbor. We put a triangle on any three vertices that share a common neighbor, and so on. And the fundamental group of this turns out to be almost the same thing as the discrete fundamental group. So it turns out to be the same as the even discrete fundamental group, which is the subgroup of even closed walks. You can show that these two groups are actually the same. And so in fact, the condition that G is simply connected is the same thing as saying that pi even G is trivial, which is the same thing as saying that the neighborhood complex is trivial. So in some sense, the main theorem I wrote down before is related to this neighborhood complex in, to be honest, a deeper way that I don't think I understand. But the reason I find this discrete fundamental group easier to work with is because, I mean, I really wanted to reason about odd cycles. And I think thinking about the even discrete fundamental groups sort of inherently doesn't talk about odd cycles and only talks about even cycles. So I personally found this version a little easier to work with. And lastly, I wanted to talk about some further directions or open problems. So currently we've got this ginormous gap between the lower bound and the upper bound for the homomorphism threshold, and which bound is closer to the truth. And more specifically, could we use approximations to the Borsa graph to bound the homomorphism threshold? So, or like, is this what achieves the best bound? So we can't do better. So yeah, sorry, I should rephrase this question. Is this graph the best that we can do for the lower bound? And we can't do better than 2r minus 1 here, because if the graph has chromatic number 2r, so this is the lowest dimension Borsa graph that'll have chromatic number 2r plus 1. And if we pick a Borsa graph that has chromatic number 2r, then it'll have a homomorphism to K2R, which is C2R plus 1 free, just because it doesn't have enough vertices to have a copy of C2R plus 1. So the question is, can you use this as a lower bound? And that would be something like, I think, R to the minus 2R. But even then, there would still be a gaping hole between the lower bound and the upper bound. On the topological side, I'm curious if there are good discrete analogs of higher homotopy groups or homology groups. Maybe these would be related to the neighborhood complex as well. And then the last question I want to ask is, I guess one can look at topological thresholds. One can ask, what is the threshold such that all H-free graphs with a certain relative degree fraction have cyclic discrete fundamental group? Or one can ask about other topological thresholds. I guess this is a little bit of an open-ended question. And I guess I've finished a bit on the early side, but please feel free to ask questions, and thank you.
Yeah, let's first thank Maya for a very nice talk. So questions?
Can I ask you something? Yeah. If you forbid not just one graph and multiple graphs, then we know whether like one of the graph determines the threshold, or is it
we don't
unknown?
Yeah, because for example, you can think about this example I gave at the beginning, where you're forbidding all of the odd cycles up to the size R. Yeah, and in this case, the homomorphism threshold for this is equal to 1 over 2R plus 1. But it seems, at least I guess maybe this isn't as good an answer as I thought, but I really don't believe that this is, I don't believe that this equality holds. I believe that the true bound is something closer to the lower bound rather than the upper bound.
Okay.
And
thank you.
So
Other questions?
So your technique is reminiscent of the simplicial complex of homomorphisms. Is there any like explicit connections to it?
What do you mean, the simplicial complex of homomorphisms?
So let me just recall. So if you have a homomorphism from a graph H to G, and then you can perturb that homomorphism by moving a vertex, say, to another one. Yeah, then it forms an edge in the simplicial complex, for example.
I see.
Yeah. So so that's basically what I recall. And yeah, you can basically build a simplicial complex out of these operations. So in a sense, if you for example, if you don't consider the insertion or deletions, and and then the length of the your walk is fixed, which means you're considering a homomorphism from a fixed length path to a graph. Yeah. Then it corresponds to the simplicial complex, for example.
I see.
Yeah.
I haven't thought about that at all.
Okay. Yeah.
Yeah, I would believe that there's a relationship. It does sound similar.
Yeah. That's what I thought. So I just but but if you haven't seen it, then yeah.
So is there any sufficient condition, some sort of reason for sufficient condition for H where if we satisfy that, then we know the homomorphism threshold is 0.
If H is bipartite. Because I guess there are only finitely many graphs that satisfy this condition if H is bipartite. But beyond that, I don't know.
I think it might be interesting because for the chromatic threshold being 0 or not for graph H, I think the deep down the combinatorial reason behind it is linked to this forbidden induced substructure and BC dimension, right? So I want to know if there's some topological reason guaranteeing the homomorphism threshold being 0.
Yeah, that would be interesting. I don't know if we know of any graph for which the homomorphism threshold is 0.
But
yeah, I guess we don't know the homomorphism threshold for any. We know almost nothing about homomorphism thresholds, so
right.
I guess we don't know any graphs that we know have homomorphism threshold 0. But yeah, that would be interesting. I'm not sure.
But wait a second, if the homomorphism threshold is 0, that means the chromatic one is also 0. Then maybe the same reason already implies that. Okay, I'm confusing myself. Okay, any other questions?
There's something in the chat, but it's not opening for me.
Sangil just said that he has to go. And thanks for the nice talk.
So if you believe the Borsa-like graph will be closer to the truth, that means this upper bound on the C2R plus 1 on R cycle the gap is huge, right? We have this 1 over linear in R and exponential in R.
Yeah. Yeah, I guess the reason I like the idea of the lower bound is because I wonder if like every sequence of I wonder if every sequence of graphs sort of has a like if you take a sequence of approximations to the Borsa graph, then topologically that sequence somehow like limits to the sphere in some intuitive way. And I'm wondering if for any sequence of graphs, there's a subsequence that sort of converges to some topological space. And so I wonder if something like that would be true. In that like the topological structure of the graph in the limit, whatever that means, is equal to some topological space. And I guess if that were true, maybe one could show that the sphere were like the topological space that maximized the min degree. But that's a pretty big idea, and it's the only idea I have for how you might show some sort of matching upper bound.
I think what you're talking about, there's a similar paper for reflexive graphs by LaRose and Tardif. In essence, they do the same thing. So they do define, similar to the Hom complex, a Hom graph, this graph of different homomorphisms of cycles. And then they take a limit of these and they show that that is categorically isomorphic to homotopy groups. So I think what you're thinking about is something similar then for irreflexive graphs. And there might be something in that direction by Tardif and Rockna. They were certainly doing, they certainly do constructions that look very similar to your construction. But
okay.
Yeah, but I'm not sure how related it would be. But yeah, thank you for the talk. This was beautiful. It's amazing. You've done really nice.
Okay, any other questions or comments? If not, then let's thank Maya again for the wonderful talk. Okay, so I think this is the last, Jungyang, right? The last online seminar